Forget the romance of the skies. Modern air combat is a game of physics and photons played out at Mach speed in a battlespace measured in gigahertz and kilometers. It is a world where victory is decided not by the pilot's daring, but by the processing power of the mission computer, the thermal resistance of a turbine blade, and the precise geometry of an air intake. In this arena, a fighter jet is the ultimate expression of a nation's will, a billion-dollar 20-ton argument forged from titanium, composites, and decades of fiercely guarded secrets. And few machines embody this brutal truth more completely than the Chengdu J-10C. Known to NATO as the Firebird, but to its creators as the Vigorous Dragon, this is the aircraft that was never supposed to succeed. Dismissed for years in Western intelligence briefings as a clumsy imitation of an F-16, a derivative knockoff cobbled together from borrowed designs and reverse-engineered parts, the J-10C has become something far more dangerous: a peer. It is the workhorse of a resurgent People's Liberation Army Air Force, play AF, a 4.5-generation multirole fighter that has clawed its way from technological obscurity to combat-proven lethality. The story of the J-10C is not just about an aircraft. It is a case study in how a nation can, through sheer force of will, industrial espionage, and staggering investment, bend the arc of technological history and forge a weapon that fundamentally alters the balance of power. This is not the story you think you know. This is the engineering, the doctrine, and the strategic calculus behind the Dragon's roar. Subscribe to the channel so you don't miss new analytical reviews. The gestation of the Vigorous Dragon was a protracted and arduous affair, a microcosm of the immense challenges that faced China's defense industry in the latter half of the 20th century. The genesis of the program, officially designated Project Number 10, dates back to the early 1980s, born from the PLAF's urgent need to replace its vast but increasingly obsolete fleets of J-7 fighters, themselves copies of the Soviet MiG-21, and Q-5 ground attack aircraft. The program was formally approved by the State Council in 1986, yet it soon languished, starved of consistent funding and political attention. The development process was slow and fraught with difficulty, a reflection of the sheer technological leap the project represented. For an industry accustomed to reverse engineering and incremental upgrades, the J-10 was a monumental undertaking. Chengdu Aircraft Corporation estimated that a staggering 60% of the aircraft's technology and components had to be entirely new, a stark contrast to the typical 30% for a new aircraft program. This figure was a candid admission of the nation's limited domestic capabilities at the time. It was the shock of the 1991 Gulf War which vividly demonstrated the overwhelming superiority of modern Western air power that renewed Beijing's interest and unlocked the necessary resources to push the project forward. Throughout its development, the J-10 has been dogged by comparisons to the Israeli IAI Lavi, a U.S.-financed fourth-generation fighter canceled in 1987. The visual and conceptual similarities are undeniable. Both are single-engine fighters featuring a delta wing and canard foreplane configuration. While Chinese officials have consistently maintained that the design is a domestic evolution of their own canceled J-9 project from the 1970s, it is widely accepted in Western analysis that some degree of technical information from the Lavi program, whether through formal or informal channels, found its way to Chengdu and likely accelerated the J-10's development. Yet to call the J-10 a mere clone is a disservice to the engineering involved. The Chinese aircraft is notably larger and heavier than its Israeli counterpart, with significant differences in its air intake and wing planform. The most formidable obstacle, however, was not the airframe but the heart of the machine, its engine. The indigenous Shenyang WS-10 Taihang engine was selected as the intended power plant back in 1983. but the program was plagued by severe developmental delays, unreliability, and performance shortfalls that almost derailed the entire J-10 project. This critical failure forced Chengdu's engineers into a pragmatic but compromising solution, turning to their erstwhile rivals in Moscow. China secured a deal for Russia's Saturn Lyulka AL-31FN turbofan, an engine originally designed for the twin-engine Su-27 flanker. Cramming this large Russian engine with its gearbox and accessory pack rotated to fit into a smaller single-engine airframe necessitated a significant and costly redesign of the J-10's aft fuselage, stretching the airframe and altering its characteristics. This dependency on a foreign power plant would become the defining vulnerability of the aircraft's early life. The evolutionary path of the J-10 is a clear illustration of this struggle. The initial production variant, the J-10A, first took to the skies on March 23, 1998, and officially entered PLAF service in 2004. It was a capable, if not revolutionary, fourth-generation fighter, equipped with a domestic Type 1473G pulse Doppler fire control radar, and armed initially with PL-8 infrared-guided missiles and semi-active radar homing PL-11s, later upgraded to carry the active radar PL-12. The subsequent J-10B, unveiled in 2008, represented a significant leap forward. It introduced a fixed diverterless supersonic inlet, DSI, a feature that reduced weight and frontal radar cross-section, an integrated infrared search and track IRST sensor, and China's first passive electronically scanned array PSA radar. However, the J-10B's production run was conspicuously short, limited to around 56 aircraft. This was likely because it served as a crucial but transitional technology bridge. The PSA radar, while a step forward, was reportedly unsatisfactory, and its development caused delays, all while the far superior AESA technology was on the horizon. The J-10B was the necessary, if imperfect, test bed that allowed Chinese engineers to master the complex aerodynamics of the DSI and gain experience with electronically scanned arrays, de-risking the far more ambitious final iteration. This definitive version, the J-10C, first appeared in late 2013 and superseded the J-10B in production from 2016 onwards. Entering combat service in April 2018, the J-10C incorporated a true AESA radar and, most importantly, finally integrated a mature and reliable version of the long-awaited domestic engine, the WS-10B, from around 2019, at last freeing the Vigorous Dragon from its Russian chains. The evolution of the fighter's air intake alone tells this story in metal. The J-10A's conventional boxy intake was a conservative design. The J-10BC's sleek DSI was a bold leap into advanced aerodynamics, a visual timeline of a nation's growing technological confidence. The airframe of the Chengdu J-10C is a masterful study in modern aerodynamic design, a physical manifestation of a doctrine that values agility and multirole flexibility. Dimensionally, the aircraft measures 16.9 meters in length, with a wingspan of 9.8 meters and a height of 5.7 meters. Its empty weight is reported to be approximately 9,150 kilos, with a maximum takeoff weight of 19,227 kg, placing it firmly in the medium-weight fighter category, broadly analogous to the American F-16 Fighting Falcon. The defining characteristic of its aerodynamic layout is the combination of a large, tailless cropped delta wing with a pair of large, all-moving canard foreplanes mounted high on the fuselage just aft of the cockpit. This configuration is inherently unstable, a design choice that grants the aircraft exceptional maneuverability and instantaneous turn performance, particularly in subsonic and transonic flight regimes. This inherent instability, or relaxed static stability, is managed by a sophisticated quadruple redundant digital fly-by-wire flight control system, which makes thousands of micro-adjustments per second to keep the aircraft stable and responsive to pilot inputs. The large canards generate powerful vortices that interact with the main delta wing, enhancing lift, especially at high angles of attack, allowing the J-10C to maintain control and point its nose with an authority that many conventional designs lack. This aerodynamic philosophy, while excellent for agility, suggests a doctrinal refusal to completely abandon the art of the dogfight, providing a potent within visual range capability as a fallback should long-range engagements be denied. The airframe is further stabilized by a large single vertical tail and two fixed, outwardly canted ventral fins beneath the rear fuselage, which enhance directional stability, particularly at high speeds. The construction of the airframe marked a significant step for China's aerospace industry, forcing the maturation of a new generation of manufacturing techniques. The J-10C incorporates a significant proportion of advanced composite materials and titanium alloys in its structure, a critical factor in reducing overall weight while maintaining structural integrity under high G loads. These materials, combined with the application of radar-absorbent coatings, also contribute to a reduction in the aircraft's overall radar cross-section, RCS, compared to its predecessors. One of the most significant engineering features of the J-10C's airframe is its diverterless supersonic inlet, DSI, inherited from the J-10B. This is a fixed, geometrically complex bump on the fuselage ahead of the engine intake, which replaces the heavy, mechanically complex, and radar-reflective moving ramps, or splitter plates, found on older supersonic aircraft. The DSI performs two critical functions with no moving parts. It creates a pressure gradient that diverts the slow-moving, turbulent boundary layer of air away from the engine intake, preventing engine stalls, and its three-dimensional shaping generates a system of conical shock waves that compress and slow supersonic air to the subsonic speeds required by the engine's compressor face. The successful implementation of this design, which requires incredibly complex computational fluid dynamics, CFD, modeling, provides numerous benefits: a significant reduction in weight, lower maintenance requirements, and, most critically, a substantial reduction in the frontal RCS by eliminating the radar trapping cavities and sharp edges of a traditional intake. The mastery of DSI technology on the J-10BC was not just an upgrade for this specific airframe, it was a crucial gateway technology, a national-level dress rehearsal that provided the essential expertise needed for the development of China's fifth-generation stealth fighters, the J-20 and J-35. Both of which rely on DSIs as a cornerstone of their low observable designs. For nearly 2 decades, the Achilles heel of China's fighter programs was the jet engine. The nation's inability to mass-produce a reliable, high-performance turbofan was a source of immense strategic vulnerability and a persistent technological embarrassment. The final integration of the domestic Shenyang WS-10B Taihang engine into the J-10C airframe was, therefore, more than a simple component swap. It was a declaration of technological sovereignty. The WS-10B is a formidable afterburning turbofan that finally provides the Vigorous Dragon with the indigenous heart it was always intended to have. Specifications indicate that the engine produces a dry thrust of approximately 89.17 kN, around 20,050 lbf, which increases to a maximum of 144 kN, approximately 32,000 lbf, with the afterburner engaged. This level of power gives the roughly 9,750 kg airframe a combat thrust-to-weight ratio greater than 1.1, enabling aggressive acceleration and sustained energy in high G maneuvers. The journey of the Taihang engine series was long and troubled. Early versions were notoriously unreliable, with a mean time between overhauls rumored to be as low as 30 hours, making them wholly unsuitable for a single-engine fighter where an engine failure is catastrophic. For years, the PLAF prudently restricted the WS-10 to its twin-engine J-11B and J-16 fighters, where the redundancy of a second engine provided a critical safety margin. The decision to begin installing the WS-10B in new-build J-10Cs from 2019 was the PLAF's ultimate vote of confidence, a high-stakes certification that after decades of investment and refinement, the engine's reliability issues had been definitively solved. This was achieved through significant advances in material science, particularly the development of third-generation single-crystal turbine blades capable of withstanding extreme temperatures, which reportedly extended the engine's service life to a respectable 1,500 hours. The adoption of the WS-10B had profound strategic implications. It unshackled China's production of its most numerous 4.5 generation fighter from the whims of Russian foreign policy and production capacity. Moscow had previously used engine sales as a geopolitical lever, reportedly tying the sale of additional AL-31 engines for other programs to a requirement that China purchase more Russian Su-35 fighters. Furthermore, reliance on a Russian engine would have severely complicated, if not outright prohibited, the export of the J-10 to third countries due to end-user agreements. The WS-10B broke this dependency, allowing China to create the fully indigenous J-10CE export variant and pursue sales to nations like Pakistan, Egypt, and Bangladesh, transforming the aircraft from a domestic asset into a tool of global strategic influence. While the standard production J-10C does not feature thrust vectoring control, TVC, the capability is latent within the WS-10 engine family. A J-10B testbed equipped with a TVC nozzle, unofficially dubbed the WS-10B3, performed stunning feats of supermaneuverability, including the Pugachev's Cobra at the 2018 Zhuhai Air Show. This demonstration signals a clear path for future upgrades, suggesting that a more agile, TVC-equipped J-10 variant could be produced if doctrinally required, further enhancing its already formidable dogfighting capabilities. If the airframe and engine constitute the J-10C's body and heart, its avionics suite is its nervous system and senses, transforming it from a mere flying machine into a lethal node in the digital battlespace of modern warfare. The centerpiece of this system is its Advanced Active Electronically Scanned Array, AISA radar, a quantum leap in capability over the mechanically scanned and passive arrays of its predecessors. Believed to be a variant of the KLJ-07A radar, this system provides the pilot with an unprecedented level of situational awareness and combat effectiveness. Unlike older radars that physically move a dish to steer the beam, an AISA uses hundreds or thousands of small transmit-receive modules to steer the radar beam electronically, almost instantaneously. This allows the J-10C to track a large number of targets, reports suggest between 15 and 40 simultaneously, while engaging multiple threats at once. Its detection range against fighter-sized targets is estimated to be in excess of 200 kilometers. Critically, AISA radars are highly resistant to electronic jamming and have a low probability of intercept, meaning they can scan the sky without easily giving away the fighter's own position. Complementing the active emissions of the radar is a passive infrared search and track IRST system housed in a distinctive dome forward of the windscreen. This sensor detects and tracks enemy aircraft based on their heat signatures, allowing the J-10C to hunt for targets without emitting any radar energy of its own. This is a crucial capability in an era of stealth, as it provides a means to detect low observable aircraft at closer ranges and allows for entirely silent, ambush-style attacks. The combination of a powerful AISA and a passive IRST networked with off-board sensors gives the J-10C a potent stealth hunter capability within a larger integrated air defense system. Data from ground-based radars or an airborne early warning and control (AEW&C) aircraft like the KJ-500 can cue the J-10C to a potential target's location, allowing it to use its ASA in a focused, high-power search or to close in for a passive IRST track, a tactic demonstrated in exercises where a J-10C successfully engaged a simulated J-20 stealth fighter. The pilot interacts with this torrent of information through a modern, AI-assisted glass cockpit designed to manage cognitive load and accelerate decision-making. The interface is dominated by 3 large full-color multifunction displays, MFDs, and a wide-angle holographic head-up display, HUD-D. All critical combat functions are managed via a hands-on throttle and stick, HOTAS control system, allowing the pilot to fly and fight without removing their hands from the primary controls. This entire system is integrated with a sophisticated helmet-mounted display, HMD, which projects critical flight and targeting information directly onto the pilot's visor. This HMD allows the pilot to cue weapons simply by looking at a target, enabling look-and-shoot engagements with high off-bore sight missiles at extreme angles. The J-10C's full potential is unlocked through its integration into a network-centric warfare doctrine. Equipped with secure, high-bandwidth data links, the aircraft can share sensor data and receive targeting information from a vast network of on- and off-board assets, including other fighters, AEW&C aircraft, and even ground-based systems. This allows for cooperative engagement tactics where one aircraft can detect a target and another, remaining electronically silent, can launch a weapon, dramatically increasing the lethality and survivability of the entire force. The aircraft is also equipped with an integrated electronic warfare EW suite, including radar warning receivers and internal jammers, and can carry external pods like the KG-600 for enhanced electronic attack capabilities. The effectiveness of any fighter is ultimately measured by the lethality of its armament, and the J-10C carries a formidable set of talons. The aircraft is equipped with 11 external hardpoints, 3 under each wing, 3 under the fuselage, and 2 smaller wingtip stations, capable of carrying an ordnance load of up to 7,000 kilos. For close-range engagements, a last resort in modern combat, but a critical capability nonetheless, the aircraft is fitted with an internal Gryazev-Shipunov GSH-23 twin-barrel 23mm cannon located on the port side under the intake. However, the true measure of its power lies in its missile systems, which are designed to give the pilot a decisive advantage across the entire spectrum of aerial combat. For within visual range, WVR combat, the J-10C's primary weapon is the PL-10 short-range air-to-air missile. This is a 5th-generation weapon, comparable or superior to Western counterparts like the AIM-9X Sidewinder and Iris-T. The PL-10 features an advanced multi-element imaging infrared IIR seeker that can identify targets by their shape, giving it all-aspect targeting capability and high resistance to countermeasures like flares. Its most lethal feature is its combination of extreme agility, enabled by thrust vectoring nozzles that allow it to execute turns reportedly in excess of 60 drones, and its high off-bore sight HOBS capability. Slaved to the pilot's helmet-mounted display, the PL-10 can be fired at targets well outside the aircraft's forward cone, allowing for look-and-shoot kills at angles greater than 90 degrees off the nose. For beyond visual range, BVR combat, the J-10C wields one of the most feared missiles in modern service, the PL-15. The domestic version of this missile boasts an astonishing range, estimated to be between 200 and 300 km, outclassing most Western equivalents like the AIM-120D AMRAAM. This extreme range is not just for engaging other fighters. Its primary strategic purpose is to threaten the high-value airborne assets, such as tankers and AWACS aircraft, that are the critical enablers of Western air power doctrine. By forcing these assets to operate further from the front lines, the PL-15 can effectively degrade an entire air campaign's reach and persistence. The missile's lethality is enhanced by two key technologies. First, its terminal guidance is provided by a miniature AESA radar seeker, which is extremely difficult to jam and offers superior performance against low observable targets. Second, it is powered by a dual-pulse rocket motor. This allows the missile to coast for a significant portion of its flight before igniting a second pulse of rocket fuel in the terminal phase, providing a massive burst of energy to chase down and destroy a maneuvering target, dramatically increasing its no-escape zone. This combination of the PL-10 and PL-15 creates a tactical dilemma for any adversary. To stay at range is to risk destruction by the long-reaching PL-15. To close for a dogfight is to enter the kill envelope of the hyper-agile PL-10 against an aircraft specifically designed for maneuverability. The J-10C is also a highly capable multirole platform, able to carry a wide variety of air-to-surface munitions. Its arsenal includes laser-guided bombs like the LS-500J, satellite-guided glide bombs, the KD-88 standoff land attack missile, and the potent YJ-91 anti-radiation missile for suppression of enemy air defenses, SAED missions. The true measure of a weapon system is its performance in the unforgiving arena of combat, or at the very least, in highly realistic combat simulations. The J-10C, as the numerical backbone of the modern PLAFIF, has been rigorously tested within China's evolving military doctrine and has seen its reputation forged in the crucible of real-world conflict, albeit under a foreign flag. The PLAF itself has undergone a profound transformation, shifting from a historically defensive force focused on territorial air defense to a modern strategic air force capable of offensive counter-air operations and power projection beyond China's borders. In this new doctrine, which emphasizes informatized or network-centric warfare, the J-10C plays a crucial role as the high-capability, mass-producible 4.5-generation fighter that complements the elite, but more expensive and less numerous, J-20 stealth fighter. Within the PLAF's highly competitive Golden Helmet annual combat exercises, the J-10C has reportedly established a remarkable record of dominance. For 3 consecutive years, from 2019 to 2021, J-10C units consistently prevailed in simulated engagements against both the larger, twin-engine domestic Shenyang J-16 and the highly vaunted imported Russian Sukhoi Su-35. The reasons cited for these victories are telling. The J-10C's lower radar signature and its more advanced sensor and weapons suite allowed its pilots to achieve the coveted first look, first shot advantage, a decisive factor in modern BVR combat. These results are less an indictment of the larger fighters and more a validation of the PLAF's doctrine, proving that in a networked battle space, superior situational awareness and stealthier characteristics can trump raw power and payload. The aircraft's combat debut, however, came not over the Taiwan Strait, but in the skies over Kashmir. In 2022, Pakistan became the first export customer for the J-10C, inducting the J-10CE variant into its Air Force to counter India's acquisition of the French Dassault Rafale. During a brief but intense conflict in May 2025, the Pakistan Air Force, PAF, made extraordinary claims that its J-10CEs, operating in a networked environment with AEW&C aircraft and armed with PL-15 missiles, had successfully shot down multiple Indian Air Force jets, including several Rafales. This alleged engagement, which would represent the first-ever combat loss for the Rafale, instantly electrified the global defense community. Pakistani sources claimed their pilots leveraged the PL-15's superior range, launching missiles from nearly 180 kilometers away while receiving targeting data from their Saab Eri and ZDK-03 Karakoram Eagle AWACS, allowing the J-10CEs to remain electronically silent. These claims, however, must be viewed with extreme caution. They originate almost exclusively from Pakistani and Chinese state-affiliated sources and lack independent, verifiable evidence. The narrative of a simple platform versus platform victory is a gross oversimplification of a complex engagement involving a multitude of assets, electronic warfare, and tactical decisions on both sides. Nevertheless, the fog of war did not obscure the strategic victory for Beijing. Regardless of the factual accuracy of the kill claims, the conflict served as the single most effective marketing event imaginable for the J-10CE. It transformed the aircraft's reputation overnight, from a cheap alternative to a combat-proven system capable of defeating top-tier Western hardware. This narrative, true or not, has fueled a surge of interest from nations seeking affordable, high-performance fighters without the political entanglements of Western arms sales, cementing the J-10C's status as a formidable new player on the world stage. In the global amphitheater of military aviation, the Chengdu J-10C Vigorous Dragon has firmly established its place not as a revolutionary outlier, but as a supremely competent and strategically significant competitor. Its value is best understood through a nuanced comparison with its international peers, where it reveals a profile of calculated trade-offs and focused strengths. Against its most direct analog, the American F-16V, the J-10C presents a compelling case for parity, if not superiority, in key areas. Both are single-engine, multirole workhorses, but the J-10C comes standard with an integrated IRST system, a capability the F-16V lacks, and boasts a clear advantage in beyond visual range combat with its PL-15 missile, which significantly outranges the F-16V's AIM-120 AMRAAM. While both aircraft feature advanced AESA radars and glass cockpits, the J-10C's Canard Delta configuration likely gives it an edge in instantaneous turn rate and high angle of attack maneuverability. When pitted against heavier twin-engine European rivals like the Dassault Rafale and Eurofighter Typhoon, the J-10C's design philosophy becomes clearer. It cannot match their advantages in payload, combat range, or the sheer redundancy and survivability offered by two engines. The Rafale, in particular, boasts a world-class integrated electronic warfare suite in its Spectra system and a significantly smaller radar cross-section, making it a far more survivable platform in a high-threat environment. Similarly, the Typhoon is a thoroughbred optimized for high-altitude, high-speed interception, and energy maneuverability, likely outclassing the J-10C in these regimes. However, the J-10C counters with its own strengths, potentially superior agility at lower altitudes, a formidable BVR weapon in the PL-15, and, most critically, a unit cost estimated at $40,060 million, roughly half that of its European competitors. It is a budget alternative with teeth, a platform that makes 4.5 generation capabilities accessible to nations without Western-sized defense budgets. The comparison with the Russian Su-35 is perhaps the most telling. In direct exercises, the J-10C has consistently demonstrated that superior integrated avionics can defeat superior kinematics. The Su-35 is a beast of an aircraft with immense power, endurance, and payload, but its reliance on a less advanced PISA radar and older generation missiles makes it vulnerable to the J-10C's combination of AESA radar, lower signature, and the lethal PL-15. The future of the J-10C is one of continued relevance, though its position at the apex of China's air power is likely temporary. The airframe has clear potential for modernization. The integration of a thrust vectoring control engine nozzle, already demonstrated, is a logical next step to further enhance its agility. Ongoing upgrades to its radar, EW suite, and the integration of even longer-range missiles are all but certain. However, with China's fifth-generation J-20 and J-35 programs now in full-scale production, the J-10C's role will inevitably transition from that of a primary air superiority asset to a highly capable multi-role supplement, much like the F-16's role in the USAF alongside the F-22 and F-35. Ultimately, the J-10C's most enduring legacy may be its disruption of the global fighter market. It occupies a strategic sweet spot, significantly more capable than lighter, cheaper fighters like the F-17, yet far more affordable and politically accessible than high-end Western jets. For nations seeking to modernize their air forces and assert strategic autonomy without being tethered to Washington's or Paris's foreign policy, the Vigorous Dragon has become the fighter of choice. It is a symbol of a shifting world order, a capable, combat-proven machine that proves China is no longer just a follower in military aviation, but a power that is now setting its own terms. It may not be the most advanced fighter in the sky, but it is arguably